Okay, so in this, we are going to first start with one question. That is the question number two, which you can see on your screen. Thevenin's equivalent. So, for this kind of questions or any kind of question, it helps to draw the diagram. So, let us quickly draw the diagram for this. So, Thevenin's. Okay, so let me. How does it look like? So there will be a voltage source in series with a resistance. So this is terminal A and terminal B, and the voltage source value is 25.1 volts, 35. Okay, so and the resistance is 35 ohms. Now this is the existing Thevenin's equivalent. Here I can connect any uh, load resistance, and I can call it whatever RL, whatever. Now in addition to this, a new what is the one? An additional 50 ohms resistance is connected across terminals A and B. Okay, so let's do that. So now the question is, what is the Thevenin's equivalent with this addition of these two? So I can draw an arrow like this. So looking towards left side, what is the voltage I will see? In the absence of this 15, I will see the voltage 25.1 because it is open circuited and like that. In the presence of 50, the VTH will be potential division. So 50 into 25.1. Okay, so here it is divided by 50 plus 35. So you know this thing, right? Any doubt in this? The voltage will be proportionally divided between 35 and 50 with this 25.1. So we will be getting something like this. Okay. So 50 into 25.1 divided by 50 plus 25. Sorry, 50 plus 35. So 14.764. And what is the Thevenin's resistance? That will be simply if I make a simple circuit, 35 parallel with 50 it will become, looking this side. So 50 into 35 by 50 plus 35. Just change this to, so 20.588. So the new Thevenin's equivalent will look something like this. Okay, that is the answer. So let's see what was asked in the question. Thevenin's voltage. So 14.76, I think, is our answer. Anyway, I'll pause it here. Okay. So here I just asked AX equal to B examples in various engineering domains. So here I got electrical, then mechanical, then civil, aerospace, chemical, controls, thermal, so and so on. So there are many applications of this AX equal to B. So I want to just quickly summarize this DC circuits topic with one example of AX equal to B. So that is why I brought this topic. So just notice this. So I go to a, no. I go to a new sheet. So think of a circuit like this, which consists of three loops. So this is loop 1, and this is loop 2, and this is loop 3. So here we can name the positions. So let's call this 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So I have three rectangular or square loops. I mean, three loops made of three squares touching each other. So if I write the numbers, it is something like this. Okay. So I want to, for this 0 to 9, that means there are 10 elements. So out of these 10 elements, out of this, I think this thing is one. You're able to, I think, some problem with the mic. Let's pause. So let's consider to fill this circuit with R's and V's. Okay. So uh, we can consider different combinations. I can consider five as resistances and five as voltages, or I can consider three as resistances and seven as voltages, or seven as resistances and three as voltages, etc. Okay. So I actually already made a problem in this. So see, for example purpose, let's take three voltages and seven resistances. So in that case, the position of the three voltages can be anywhere, and the remaining will be resistances. Okay. So I'll show an example. I think I already opened it. So here you can see on the board. You can see here. So there is a circuit with the same structure. There are three voltages, and remaining seven are resistances. Okay. So if you see, this is randomly generated, and there are. This is like, if you notice on the right, you can see extreme. There's a page number 19 actually. So I'll go to the previous page. So here again, you can see uh, the voltages and resistances are still there, but in different positions. Okay. So it's all randomly generated things. Okay. So the question is, how many combinations like that you can make? So there are 10 positions, out of which 3 I want to allocate to voltages, and remaining 7 I want to allocate to resistances. Okay. So, so if I keep the problem this way, so if I want to make a list like this, maybe V, R, R, V, R. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and last will be R. So this will represent one one combination, right? So if I shuffle this list, okay, so right now it is V. So from this, what I'll get? So at position 0, V is there. So there is a voltage source. So the direction, again, I can assume anything. I can. Then at position 1, we have resistance. At position 2, we have resistance. Position 3 is again a voltage. Okay. Position 4 is a resistance. Position 5, resistance. And 6 is again voltage. 7, 8, 9 is again resistance. Okay, so like this, we get one circuit like this. If I shuffle this list, then maybe some other randomly shuffled. So let's say R, R, one more R, V, V, R, R. One, 2, 3, 4, 5, 6, 7, 8, 9. So last one should be has to be V. Okay. So then how does this look like? So position 0 is resistance, resistance, resistance. This is also resistance. This one is voltage, and this is another voltage, and this is resistance, and this is a voltage, and this is a so on. Okay. So you got the idea, right? So my question is, how many ways this thing is possible? How many ways we can define this RR or VVV? What, you forgot the max? Okay, let me ask very simple way. Let's say I start with the V. Okay, how many possibilities are there to select V? So first V I can allocate in 10 positions, right? So I start with all 6, 7, 8, 9, 10, 10 empty spots. I want to allocate V there. So V can go in 10 positions, right? Anywhere. So let's say I go here like this. So the first one has 10 options, second one has 9 options, and the third voltage has 8 options. So 10 into 9 into 8. Okay, so what is 10 into 9 into 8? So 9 into 8 is 72, into 10 is 720. Okay, so we get 720 ways in which I can spread the voltages in the circuit, and the remaining all will be R's. Okay? So if there are 400 students, I can still give unique circuit to each student because total combinations here are 720. Anyway, you're following what I'm telling, right? Okay, so correct. So now, if we assume that each resistance is again different, okay, then it will be even different. 10 factorial is saying, which is a very high number. Okay. So meanwhile, what I did, I considered that there are 10 elements, out of which 3 are voltages, 3 are currents, but all their values are two-digit numbers. Okay, between 10 to 99, two-digit numbers I can assign anywhere. Okay, so again, each one, see this V can be anywhere between 10 and 99. Okay, so on. So now you calculate. There are almost like it goes into billions of combinations. So now I'll quickly show you a program. So this is a 50 pages PDF, right? So 16, 14, 13, 12, like that, different pages, different you're getting, right? So we can, so what you see on the left side of the screen, this one is the actual program. Okay. So for example, here you can see I have taken here this line. I have taken three V's and remaining all R's. And then I am going for shuffling it. Okay. In Python programming, how many of you know Python programming? Okay, so quite a few people know. Very good. So I shuffle it and return that list. Okay, and this one you see, I am generating two-digit random number between 10 and 99. Okay, so and because I have 10 elements, I'll get 10 this thing. And here I can give number of questions, how many I want, and then this is the place where I am drawing the circuit. Okay, so for example, if you see coordinates, okay, I'll quickly show the coordinates also. So so obviously this is 0 comma 0, and this is 0 comma 2. So this is 2 comma 0, 4 comma 0. So like this we can build the coordinates, right? What is this one? So 2 comma 2. So you see the element number 0 is present between these two coordinates. Element number 1 is present between 2 comma 2 and 4 comma 2. Element number 2 is present between 4 comma 2 and 6 comma 2, and so on. Okay, so now if I see here in this code, so here you can see 0 comma 2 to 2 comma 2, there is one value r. 2 comma 2 to 4 comma 2, like this. So there are these 10 elements. I'm just we have to draw the circuit like that. Okay? So again, if you don't, you need not worry, I'm just showing how this particular diagram has been generated. So but obviously here if you notice, everything is r. So all 10 are our default values. So three of them I will convert to V. So how I convert to V? So if you go down, so here you can see here there is a if condition. So if the element is V, then I change it to a battery symbol. Otherwise, it remains as a resistance symbol. So that is how it is. And finally, it is returned to a file called circuit.txt, and then I'm converting into PDF using this command. So it will come, and it's a for loop. So if I give number of things, it will generate. Okay. So now the question is, so now you know there is almost billions of combinations possible to make a circuit. So now the question is, uh, how do you solve this? So for solving this, I think some of my videos have mentioned what is called as a loop current method. Okay. So let's explain that. So I think better to take a example. So I'm just taking one example. So this one I'll take. So I'm drawing the circuit here. Sorry, that is resistance. Okay. So here we mark three loops. So this is called loop one. Let's say the current here is I1, and this is called loop 2. The current here is I2, and this is the loop 3. The current here is I3. So we have three rectangles or three squares. In the three loops are there, three currents I've identified. Now we can write KVL. Okay, so Kirchhoff's voltage law. KVL for each loop. Okay. So what I will do, I will directly, maybe here I will write. One thing you should notice here, for example, this the one branch which is common between loop 1 and loop 2. So the current in that will be I1 coming downwards and I2 going upwards. Okay, so I1 minus I2 will be the current in this, whereas this side all the current is only I1, and this side the current is only I2, and so on, like that. Okay, so the objective now is to find out the values of I1, I2, and I3. Okay. So maybe I will directly write it in this way. So I1, I2, I3. So these are the three unknown values. Okay. So I'll get a matrix here. Okay. So for the first equation, I will take the first loop. Okay. So in the first loop, let's say I start at this corner. I can start any corner. One corner I will start and complete one loop. Okay. So we'll apply Kirchhoff's voltage law. So if I start moving towards the right side, I'm jumping from positive side to the negative side. That means the voltage is reducing. Okay. So here it will become minus 25. Okay, because this is uh, okay. So it should be minus 25 on the left side. So whereas on the right hand side it becomes plus 25. Okay, to avoid confusion, I will write here. And we are at this point now. Then going downwards, so it will be, so this is the current and the resistance is 72. Okay. Then going this side, so it will be minus 90 into I1. Then going upwards, it will be minus 72 into I1. All of this will be equal to 0. So this is the first equation. The same thing I will write directly here. So what I will say, all the voltages will be uh, transferred to the right hand side. It will become the B matrix or B vector. And here, let's make a grid kind of thing. So which are the elements common between the loop 1 and loop 3? So there is nothing common between loop 1 and loop 3. So this will be 0 and this will be 0. Okay, so that is how we build this. It finally comes to that. I'm just giving the shortcut step. Which are the elements that are common between 1 and 2? So the 72 is common between loop 1 and loop 2. So that will come here. The question is whether it will be plus or minus. So here, if you see, this minus gets multiplied with this minus and becomes plus for the I2 term. Okay. So whereas this 72 is going to multiply with I2, right, in the matrix multiplication. So that is why it is plus. Okay. Same way for the equation for the second loop. So here 72 will be there. Okay. So because 72 will get multiplied with I1 and it will be positive. Because when I write the equation for the second loop, the current will be I2 minus I1. So that way. What is common between 2 and 3? We have 62, which is common between 2 and 3. So, like this. And what is all the resistances touched by loop 1? Okay, so that will be here. So, minus of 72 plus 90 plus one more 72. Okay, so, here you can see this 72 is there, this 90 is there, this 72 is there. These are all the resistances in the first loop. Okay, so that way. Can you now see what is there here? So it will be minus of 72, 25, 62, and this one, okay, 62, 98, and 30. Okay, and now coming to voltages, what are all the voltages in the first loop? So here we need to be careful with respect to the sign. Okay, so it will be minus 51 in the second equation and it will be 54 in the third equation. So this is how my AX equal to B has come into picture. So this matrix is called A. Okay. So what is the A matrix? So 72, 72, 144, 90, 234. So minus 234, 72, 0, and it will be 72, 62, 0 here, 70, sorry, 62 here, 72, 25 is 97, 99, 159, I think. And this one will be 98 plus 62, 160, 190. Okay, so like this, I got a matrix. So sorry, here I1, I2, I3. All of this is 25 minus 51 and 54. Okay. So at this moment, I'll just quickly go back to our answer, not this. So here you see, uh, so different engineering I have told, right? So admittance or impedance matrix. Okay, so whatever that A matrix we considered, it is called admittance matrix. Okay. Voltages or currents, and then independent voltages are. So here you see B is the vector of independent voltages or current sources. Solving resistive circuit with multiple nodes to find unknown voltages or currents like that. So same way you can find in various other domains also, mechanical, civil, aerospace, and so on. Okay. So how do you solve this? Sorry, I have to be back here. So again, as I think last week also I did. Do you know how to invert a three by three matrix? So what if it is a matrix of larger dimension? So for example, what if I consider something like this? Okay, I'm not going to solve the other problem. So what if I consider the network with some structure like this? So maybe like this, like this. Okay, so here I have six loops. So you'll get six by six matrix. So you will get something which is six by six, and you will get six unknowns here and then six constants here. So you should be able to again invert this six by six matrix. How many of you know how to invert a six by six matrix? Okay. So we have to use a calculator or a computer or a software to do that. Manual hand calculations, it is highly, I mean, it can be done, but it is highly difficult. Okay. How many of you are from AI here? AI department? Nobody? So again, AI also same thing, matrix multiplications, and so on. Almost all the methods there use this only, matrix multiplication. So anyway, whenever you see a circuit like this, you should be able to quickly make the AX equal to B and complete it. Okay, should I proceed further? Any questions you want to ask so far based on what I was generally talking about? So what happened to my earlier? Okay, I think it's gone. Yeah. Any questions you want to ask here? So what I was trying to attempt was something like this. So this is a 50 pages PDF, right? So I want to build a circuit, solve it, and write the answer below, and go to the next page, build one more circuit, solve it, and write the answer below, and so on. Okay. So it need not be 50 pages; it can be 500 pages also. Okay. So if you are interested in knowing how to solve this and all, let me know. Okay. So. I think this part, explanation of this part, I will stop here. I believe you got some idea. So, okay. So, just in the end, we will discuss last one question. That is question number 20 that you are seeing on the screen on the left side. Okay. Find the Norton's equivalent IN when seen from the load terminals A and B. So, what is the Norton's equivalent? So Norton's equivalent, okay. So Norton's equivalent is like same as Thevenin's equivalent, where Thevenin's equivalent will be looks like this. So this is one and this is two. Okay. I think I can increase the height. So Thevenin's equivalent looks like this: a voltage source in series with a resistance VTH and RTH and A and B terminals. And Norton's equivalent looks something like this: a current source in parallel with a resistance. Norton's resistance and IN, Norton's current. So both these circuits actually behave similarly. For example, uh, here obviously there is no current because it is open circuit. Here also it is open circuit on the right side, whereas on the left side, of course, there will be some current continuously flowing all the time, in this loop. Okay. So the moment I connect a load here, so let's say resistance of 10 ohms I connect here, how much it will take the current depends on the values of VTH and RTH. The same 10 ohms, if I connect on the Norton's equivalent also, the idea is the current calculated on the left side and the current calculated on the right side both will show equal value. Okay? That means it behaves exactly same. The two circuits behave exactly the same. In fact, not only these two circuits, there is actually a larger circuit. So, for example, there is a larger circuit. In the larger circuit, something like this, I can identify two points. So let's call this point A and let's call this point B. And whatever this element here, I can remove that, and then the rest of the circuit can be represented as a Norton's equivalent or Thevenin's equivalent. So that is the idea. So for example, even if I go back to this one, okay, let's say if I consider 12 ohms here as the my load resistance, I can define this point and this point as A and B. For the entire circuit, I can make a Norton's equivalent or Thevenin's equivalent. Okay, so just to repeat the point, so if I remove this 12 ohms and consider this as A and B points, I can make this entire circuit as a single this one. So actually, it is nothing what you call new. You know how to convert three equations into one equation by knowing the values and assuming the introducing new variables and all this. So that is what is done here. Anyway, let's not go into the theory like that. Let's come to our specific question that we are solving. That is this question number 20. Okay, let's uh, sorry, let's draw that. So I'm trying to scroll this. Okay, this one may be for scrolling. I think I'll go with a new one. Okay, so let's solve question number 20. 12, 65, 22. Sorry, that is 12, right? This is 22. 4. Here also one 12 ohms is there. Here 4 ohms is there, right? And this two terminals are my terminals for which I want to calculate the Norton's equivalent. Okay, so that is a question. So the thing is, the Thevenin's resistance is same as Norton's resistance. Okay, so simply first step one, find Rn. Norton's resistance or Thevenin's resistance. Both are same. So what you do, you short circuit the voltage sources. So I start with A, and I have 12 ohms here. This one is short circuited. One more branch, there is another 12 ohms, and here 4 ohms is there on this side. Okay. So if you notice, 12 and 12 are coming in parallel, and 4 is coming in series. Okay. So 12 parallel 12, it will become 6. In series 4, it will become 6 plus 4, 10. So Rn is nothing but 10 ohms. Okay, so that is the first part. Next, find out the Norton's current. Okay, what is Norton's current? So if I short circuit this, how much current would flow? That current is called Norton's current. That is the definition of Norton current. Okay, In is nothing but short circuit current. So I just short circuited these two. Okay. Now the problem here is I have two loops. Okay. This is loop one, loop two. Two voltage sources are there, and I'm supposed to find this current. Okay. How do you find? So you can write two equations, two unknowns, you can solve it, or you can use superposition theorem to solve it. Okay. So let us use superposition theorem. Okay. So what you'll do here, so first consider only 65 volts. Okay. So one voltage source I'm considering. So this is 12, and this is 12, and this is 4, and this is short circuited. So question is, what is this current? Okay. So 12 parallel 4, I need to calculate. 12 into 4 divided by 16. So this is 3 ohms resistance. So this side is 3. 3 plus 12 is 15. Okay. So total R total is 15. V is 65. So current total will be what? V by R. So 65 by 15. So how much is that? 65 divided by 15. So 4.3. So that is here. 4.333 is here, which is splitting into two paths. One path going here and other path going here. Current division principle you have to use. So I1 will be equal to this 4.33 multiplied by opposite resistance is 12. Total resistance is 12 plus 4, 16. Okay. So again, so let's calculate that. Multiplied by 12 divided by 16. So that comes to 3.25. Going towards the right side. Okay. Now what is the next step? Repeat the whole process with 22 ohms resistance. Again, you will get one more current. Okay. Actually, taking the symmetry of the circuit, I can do one thing. See, this is 12, this is 12. So the whole thing will be same. Only thing is this will be replaced with 22. Okay. So I2 will be proportionally reduced. I mean, I'm not proving this anything. I'll just because time is getting over, I will do like this. Okay. So because voltage is reduced by some factor, current also will be reduced by the same factor. So this is I2, 3.25, 22 by 65. So into 22 divided by 65. Okay. So 1.1 is the another current. So what is the total Norton's current? 3.25 plus 1.1. So it will be 4.35 amperes. So this is your final answer. Okay, so let's check. Yeah, so we have that as option C. Okay, so option C is the correct answer. So anyway, so I'll stop here. Thank you.